The question is, a particle of mass m is moving in a straight line with momentum p. Starting at t is equal to 0, a force F is equal to kt acts along the direction of motion of a particle for the time interval capital T so that its momentum changes from p to 5p. The value of t is. Alright, so there is a time varying force acting on a particle, then there is momentum change, and we need to find out what is the time interval. So it's an interplay of force, change in momentum, and time. Alright, so not difficult to guess at all that the relationship that is going to help us is F is equal to dp by dt. Now intentionally I have removed the vector notation because everything is happening in a straight line. So F is equal to dp by dt. Alright, this tells me that dp is going to be equal to F dt. Now you know we are going to integrate on both sides. So dp integral is going to be F. I know F is equal to kt. So kt dt. Now the limits. So the force starts acting at t is equal to 0, and at that instant the momentum was p. Now at time t, the momentum has become 5p, hence these would be the limits of integration. Okay, so integral of dp is going to be p, and the limit has to be put from 5p to 5p, and then k is a constant, and then t dt integral is going to be t square upon 2, and limit has to be put from 0 to capital T. Now let's put the limits. This is going to become 5p minus p, which is 4p, and this is going to become k divided by 2 into t square. So what I'm going to get is t is equal to 2p upon k under root multiplied by 2, and that is going to be my answer. Pretty straightforward question. Let's have a look at the options. So option C is going to be the right option. If the thrust on a rocket moving with a velocity of 300 meter per second with respect to the propellant is 210 Newton, the rate of combustion of fuel is. Alright, so there's a rocket, and how does the rocket get its thrust? The rocket expels these propellants. These are the fuel or gases that come out. Okay, so we know that the thrust is 210 Newton, and the relative velocity of the rocket with respect to the propellant, these gases which are being ejected, is 300 meter per second. We have to find out what will be the rate of combustion of the fuel, or basically what we mean is that what is the mass of the fuel per unit time being ejected by the rocket. Is that correct? Okay, so we know that very well, that the thrust acting on a rocket is equal to the relative velocity multiplied by dm by dt. That is the rate of mass change. Okay, so we know that F thrust is 210 Newton. We also know that relative velocity is 300 meter per second. So this multiplied by dm by dt. So from here I'm going to get dm by dt is equal to 210 upon 300. So 0 and then 37 and 310. So this is going to be 0.7, and the unit obviously is going to be kilogram per second, and that is going to be my answer. All right, let's have a look at the options. So option C is going to be the correct option. The question is, a rigid ball of mass m strikes a wall at 60 degree and gets reflected without loss of speed as shown in the figure. All right, so you can see by this animation what is happening. The value of impulse imparted by the wall on the ball, excellent, will be. Alright, so this strikes at an angle 60 degree, gets reflected at an angle 60 degree, and without loss of any speed. So if the speed here is v, the speed here is also going to be v. We need to find out what is the impulse by the wall on the ball. Okay, so first of all, what is impulse? Impulse, we know, is the change in momentum, and impulse is a vector quantity because momentum is also a vector quantity. Hence, we need to be very careful when we are calculating impulse or change in momentum. All right, so whenever we have vectors, the easiest thing to do is, well, not the easiest, I think, but the most foolproof way of doing it to use vectors. So I'm taking x-axis like this, and I'm taking y-axis like this. That is my choice. You can choose your axis as per your convenience. So what I'm going to do is I'm going to write what is the initial velocity. Okay, now velocity is like this. So you can see that the component perpendicular to the wall is going to be v cos 60 degree. and parallel to the wall is going to be v sine 60 degree. And similarly, we have also broken it down for the final velocity. So the initial velocity is going to be, or I should directly write initial momentum, right? Why do the hassle of two steps? Okay, so the initial momentum is mass times velocity. So this becomes mv cos 60 degree. Okay, but what is the direction? It is minus I cap. Okay, plus mv sine 60 degree. And what is the direction? The direction is j cap. Is that correct? Can I also write the final momentum in the same manner? So what is happening to the final momentum? So mv cos 60 degree, and what is the direction? It is I cap, plus mv sine 60 degree multiplied by j cap. Is that correct? Okay, so what is the change in momentum? The change in momentum is P final minus P initial. So if we subtract this from this, what we see is mv sine 60 degree j and mv sine 60 degree j gets cancelled. So what am I left with? So from here, minus I will become plus. So I'll be left with 2 mv cos 60 degree I cap. Is that correct? So cos 60 degree is half. So 2 and cos 60 degree is going to give me 1. So the change in momentum or the impulse is mv I cap. Perfect. Now we need to find out what is the magnitude. So the magnitude of impulse is equal to mv. All right. Now this is a slightly longer way of doing it. The simple way, the very simple way is that any velocity perpendicular parallel to the wall, okay, there will be no change in velocity parallel to the wall. Look here and here, correct? Because there is no force acting parallel to the wall, which means that v sine 60 degree will have no consequence on the change in momentum at all. Okay, now this is v cos 60 degree and this is also v cos 60 degree, and we know that they are in opposite directions, which means that the difference between these two quantities is going to become 2v cos 60 degree. Okay, so you need not use vector all the time, but you can, by just using common sense, you can solve this question much quickly. All right, now let's have a look at the options. And option A is going to be the right answer. The question is, a man mass 70 kg and his son mass 20 kg are standing on a frictionless surface facing in same direction. The man pushes his son so that he starts moving with a speed of 0.9 meter per second with respect to man. The speed of man with respect to the surface is, all right, so there is a frictionless surface and a son and his father are playing, and the man pushes his son with a velocity relative to himself. All right, this statement is very important. So he pushes with some velocity relative to himself. So when he is pushing his son, obviously he is going to experience a force back towards him, and he will also move on in the opposite direction. Okay, we need to find out what is the velocity of man with respect to the surface. So for clarity, I'm denoting surface by ground, and that's why I've written it as g. Okay, so velocity of man with respect to ground, and this is the velocity of sun with respect to man. All right, that's what we need to find out. Okay, now this is a frictionless surface. Is there any force in the horizontal direction? And I'm talking about external force in the horizontal direction on the system. So the system is man plus his son. On this system, is there any external horizontal force? None. I can't see any, which means that the linear momentum in the horizontal direction is going to be conserved. Now, linear momentum is going to be conserved, but about which frame? All right. Is it with respect to the man, or is it with respect to the surface or ground? So the ground here is stationary, hence that is the inertial frame. The man is not an inertial frame. So we have to conserve linear momentum about the ground. Okay, which means that the mass of the man, okay, multiplied by the velocity of man with respect to ground, that is the momentum of the man, plus mass of sun into velocity of the sun with respect to ground. Correct? We have to conserve it about the ground. So this is the linear momentum of the sun and man as a system. And what's the initial linear momentum? 0, because they were at rest. So this has to be equal to 0, and that is what I need to use. All right, very well. Now, since we are dealing with vector quantities, we need to choose a direction as positive. So rightwards we have chosen as positive. Okay. So for simplicity, what I can say is, let's say v is the velocity of the sun with respect to man, and we have assumed it in the rightward direction. Okay. And capital V is the velocity of man with respect to ground, and that we have assumed in the leftward direction. Is that correct? Now what we need is, we need to substitute. Okay, so mass of man into velocity of man with respect to ground. So velocity of man with respect to ground has a magnitude v, but what is the direction we have assumed? Towards the left. So I will have to substitute minus v, plus mass of the sun multiplied by velocity of sun with respect to ground. What is this velocity? Is it the velocity of sun with respect to ground? Not at all. It is the velocity of sun with respect to man. Can I substitute it in this equation? No, I cannot. If I do that, I'm going to make an error, which means I have to find the velocity of the sun with respect to ground. And for that, I need the relative velocity relationship. So velocity of sun with respect to ground will be equal to velocity of sun with respect to man plus velocity of man with respect to ground. This is what I will have to substitute. All right, this quantity right here. Okay, so velocity of sun with respect to man is v. What direction we have assumed? Rightwards. So this becomes plus, and then plus velocity of man with respect to ground. What is this? That is capital V. But in which direction? In the leftward direction. So I will have to substitute minus v, and this is going to be equal to 0. All right, be very careful that the substitution or the linear momentum conservation has to be done from the ground frame. Okay, so now we have minus mm plus msv. Okay, so we have a capital V here as well, and then we have minus ms capital V, and this is equal to 0. So V comes out to be, and I'm talking about capital V, comes out to be msv upon mm plus ms. Right? That is going to be the speed of the, or velocity of man with respect to ground. Now ms is how much? Ms is 20 kg multiplied by velocity of sun with respect to man is how much? It is 0.9 meter per second divided by mass of man plus mass of the sun. Okay, so this is going to come out to be 20 into 0.9 upon 90. So from here, this decimal goes, and then I have 10 over here. So I will be left with 0.2 meter per second. Now this velocity comes out to be positive, which means the direction we have assumed is correct. If this would have come out to be negative, which means that the direction would be opposite. Okay, so what is the velocity of man with respect to ground? It is 0.2 meter per second. Which direction? The leftward direction, and that is going to be my answer. All right, let's have a look at the options. So 0.2 meter per second, option A is going to be the right answer. What is the percentage increase in length of a wire having diameter 1.5 millimeter stretched by a force of 50 kilogram weight? Young's modulus of elasticity of wire is 15 into 10 to the power 11 dyne per centimeter square, and G is 10 meter per second square. All right, so there is a weight of 50 kilogram weight, which is nothing but 550 into 10 and 500 Newton. All right, this weight is acting, and hence there is elongation. We have to find out what is the percentage elongation. So if fractional elongation is going to be delta L by L, then the percentage elongation is going to be delta L by L into 100, and that's exactly what we need to find out. Now Young's modulus is given to me in dyne per centimeter square, so obviously I will have to convert that into Newton per meter square. So 15 into 10 to the power 11. Now dyne is 10 to the power minus 5 Newton, and centimeter square is 10 to the power minus 4 meter square. All right, simple way to convert that. So this becomes 10 to the power minus 1. So this is going to become 15 into 10 to the power 10, Newton per meter square. All right, just converting the units. Okay, now what do we have? We have the Young's modulus is equal to the stress divided by the strain. So from here we get delta L by L is equal to F upon A Y, and that's basically what we need to find out. Okay, so what is F? F is 500 Newton divided by A. A is going to be pi d square upon 4. So pi into d square. What is d square? 1.5 millimeter square. So multiplying it by 10 to the power minus 6 gives me meter square, and then divided by 4 is going to go up. And then what do we have? We have the Young's modulus, which is 15 into 10 to the power 10. All right. So 2 zeros. So this I can write it as 2000. So 3 zeros from here, and this becomes 10 to the power 7. We have 10 to the power minus 6. So this becomes just 10. Okay. So if I calculate this, so this is going to be delta L by L. What we need to calculate is delta L by L into 100, which is the percentage. So I can multiply this term by 100. So in that case, I will be left with 2 into 10 divided by 3.14. And then we have 1.5 square, which is going to be 2.25. And then we have 15. Okay, anything else which gets cancelled? So 5, 2, and then we have 5, 3. So this becomes, taking this calculation over here, this becomes equal to 4 divided by, so 3.14 we can approximately take it as 3. So we have 9 in the denominator, and then we have 2.25. Okay, so this becomes 4 upon 9 into 5, 45, 9 2s are 18, 22, 9 2s are 18, 20. Okay, so 4 upon 20.25. Okay, now if this would have been 20, then my answer would have been 0.02%, but this is 20.25, which means it will be slightly less than that. So approximately the answer will come out to be 0.19%. Is that correct? A little bit of calculation, but we can handle that. Okay, so the correct option in this case is going to be option 1, 0.19%.